Well, I have to say that I am really happy to be here because in my 11 years at the university, I think this is the very first time that I have a chance to tell my colleagues about my work. So thank you, Marty, for the opportunity. This is really, hopefully, enjoyable for everyone. So I want to talk today about pleasure systems in the brain, and I want to start with a story. In the 1950s, psychiatrist Robert Heath started a controversial program to implant electrodes in the brains of patients that suffer from epilepsy, depression, and schizophrenia. He had good intentions. He wanted to find the area of the brain that maybe was the cause of some of these disorders and maybe find a solution and a cure for these patients. He claims that he had a great success, but that success was short-lived. So he would implant the electrode, activate electricity, and patients felt better. They claimed that they felt better. So in order to extend the benefits of the electrical stimulations, he allowed patients to press a button to receive electrical stimulation. Some of these patients press as many as 1,500 times in the course of 3 hours. And he said, what might be the reason why these patients are pressing so much? It must be that they like it. And he claimed, I found the pleasure center. It turns out that 40 years later, today we know that he had not found the pleasure center. There were other reasons why these patients were pressing the button to get this stimulation. But me and others have actually been very much involved in trying to find out what are those brain substrates and neurochemical mechanisms that produce pleasure in humans. So my story is a story about rats. It's not a story about humans. And the first thing that I have to tell you is how I measure pleasure in the laboratory. So if your subjects are humans, then it's an easy task. You just ask them, how pleasurable is this? How much do you like this? But if your subjects are rats, the story is a little bit more difficult. And one solution to this problem came from research by Jacob Steiner at the Hebrew University in Israel. And in the 1960s, and actually 1970s, he actually gave a pleasurable taste sugar to one-day infants, newborn infants. And he actually found that these infants would elicit these reactions that reminded a little bit of smiles in humans. And if the taste was an aversive taste, actually quinine, then the reactions were completely different. It turns out that these reactions are not only present in humans, they're also homologous in other species, and they're also present in rats. So this is a rat that is receiving sucrose directly to their mouth, and this is a rat that is receiving quinine. And you can see the comparison and the similarity between these reactions. So maybe more exciting is if I actually can show you a video of a one-day newborn baby that is receiving sucrose. They are rhythmically licking and taking their tongues out, tongue protrusions. This is actually a primate that is also receiving sucrose, and this is a rat. They are all receiving sucrose and producing similar reactions. When we look at aversion, we see these triangular mouth faces, shapes of the mouth. Yeah, they're clearly not liking it. This is not the only reaction that they elicit. This is one of about 5 or 6. They can also move their limbs. They shake their heads trying to get the solution out of their mouths. And the rats do exactly the same kind of rats. Now, if we look at humans, there is no question of what is the pleasurable reactions and the aversive reactions. There is no question about it. When we get to the rats, we see the same kind of reactions. We tend to imply, or we have to guess that these are telling us something about the effective value of the solution that they are receiving. They're not simply ingestive or rejection reactions. They tell us something about the effective quality of what they're experiencing. As it turns out, these reactions actually are quantifiable, and they increase or decrease with procedures that would increase and decrease pleasure in humans. So for example, when we are hungry, food tastes better. And when rats are hungry, these reactions also increase in number. If we pair a taste with sickness, we don't like that food. And in rats, if you pair, let's say, sucrose with sickness, they completely reject the food, even if it's sucrose, a very palatable food. And the sucrose no longer produces positive reaction, they produce negative reactions. So we have really, good reasons to believe that this measure is actually a measure of pleasure, not just a measure of ingestion or rejection. So I'm going to tell you some of what we have found using this technique about measuring taste pleasure in animals. In a nutshell, I can tell you that, by the way, this is a sagittal view of the brain from the side. This is a rat brain. And we have identified three structures: the nucleus accumbens, the ventral pallidum right here, and at the back of the brain, the parabrachial nucleus. All of these structures are causally involved in the increase of hedonic reactions to sucrose when we stimulate them chemically. I'm going to say this one more time because you probably didn't process any of that. These three structures, we think, are causally involved in the production of pleasure. When we experience pleasure, they don't just light up, they don't just simply correlate with the experience of pleasure. We think that they actually cause the pleasure that one experiences, okay? And I want to be a little bit more specific, and I'm going to tell you about one of those structures and how we went about deciding that these structures are actually causally involved in pleasure. This is a cross-section of half of the brain. So through here, just half of the brain. And this is an area of the brain called the Nucleus Accumbens. You might have heard about this in your Psych 101 classes, if you remember any of that, okay? So I am particularly involved in this reaction because when this area, because when you stimulate this area, the animals are very engaged and are very focused in obtaining a reward. So we wanted to see if this area was at all involved in pleasure. So what we do is we chemically activate this structure, in this case with opioids. Opioids are drugs like morphine, for example. In my case, I use a particular drug called Damgo. So what you see here is a blown up version of the nucleus accumbens there. And you see these hexagons that reflect individual microinjections in the brain. We know how far away the drug is activating neuronal substrates because we can measure this with something called immunohistochemistry. You don't need to worry about that. Just know that I have a measure of knowing how far the microinjections are activating the brain. And the colors, I don't want you to be confused, this is not a neuroimaging slide. You know, we don't do that in rats, we do it in humans, but not in rats. The colors indicate increased numbers of hedonic reactions. So right here, in the front of the nucleus accumbens and in the dorsal part, in a highly localized area that in humans is equivalent to a 1 cubic centimeter in humans, but in rats is 1 cubic millimeter. When we inject opioids here, we see an increase of about 200% in the number of hedonic reactions. So we think that this area is very much important for the causal production of pleasure. And this, by the way, this in red here is meant to represent this hedonic hotspot, we have called it. A hotspot because we think it's very important for the production of pleasure. It's very different from the map behind in green. We find a dissociation between pleasure and desire in the brain. While the red identifies pleasure, the green is meant to represent wanting or desire. So we find this dissociation here. In a nutshell, I'm going to tell you one more time that these are the three structures that so far we think mediate pleasure using the same techniques that I have described. We have identified three different neurochemicals: opioids, cannabinoids, and benzodiazepines. We know that these circuits that these structures are part of the same circuit because when we activate one, we see also activation in the other ones, and if we block one, we block the increase in pleasure. So all three of them are seen to be somehow connected, and there is anatomical evidence that these structures are indeed connected, and we think that they're indeed part of this pleasure circuit. Am I going to get the award today? Am I going to get the award? It looks like. Maybe I'm going to skip this last part. Some of you might be wondering, wait a minute, you haven't really said absolutely anything about dopamine. And I've heard many times that dopamine is involved in pleasure. If you took Psych 101 and studied anything about pleasure, they probably told you that dopamine is involved in pleasure. I have done about 4 studies related to this story, and today is widely accepted that dopamine is not a pleasure neurotransmitter. Very briefly, I'm going to tell you about an experiment that I did with genetically manipulated mice that had high levels of dopamine. In fact, these animals are very much focused on getting a reward. I tested them in a runway. The mouse is here. I raise a door. They run to get a Fruit Loop. These mice love Fruit Loops, and they're cute as they can be when they eat them. They hold them with their little hands, and they absolutely love it. When we look at how quickly they go to get that reward, the extra dopamine mice go very fast, much faster than the controls. They are less engaged in pauses or in reversals, so they're very much focused to get the reward. But when we look at these affective reactions, the hyperdopaminergic mice actually show less hedonic reactions than the control mice. Again, they're invested in getting the reward, but they're not experiencing more pleasure once they get it. So the conclusion is that pleasure, we think, is generated by a network of highly localized opioid, benzodiazepines, and cannabinoids hotspots. These hotspots include the Nucleus Accumbens, the ventral pallidum, and the paravertical nucleus. And dopamine is not a pleasure neurotransmitter. This research is important because this function of pleasure is at the root of many psychological disorders like depression. It's also at the root of other disorders, maybe like obesity and substance abuse. And thank you to the many collaborators that have been participating in some of these experiments also.